Okay. Is this working? Start video, fool. Failed to start the video camera. Please select another video camera. Why? USB video. Oh, no, integrated webcam, you dumbass. Start video. There we go. Okay. So you guys should be able to see me now. Sorry about that. My laptop actually died over the weekend. So in addition to all that crazy on-a-lock bullshit, I had to figure that out. Right now I'm using my computer from my office, which I stole from Santa Fe with their permission. So things are a little bit different, and I've been having a little bit of software troubles from time to time. But I think I got all the kinks ironed out this morning. Everything should be working now. Got the doc cam fired up. We're set up through the VPN so Santa Fe can watch everything I do, and that makes everybody happy. I want to do a few things today. I'm going to talk about the exam a little bit, but I also want to introduce the new material because we're opening the middle third of this course, which is the most badass part of this course by far. Because it's all about convergence. So let me swap to the doc cam. This is, of course, MAC2312. Today is the 24th. So there are still some folks who haven't taken the exam, so I'm a little bit reluctant to run straight through all of the questions. You should have answers to all the true, false, and multiple choice automatically. If anything in there looks weird, we can talk about it. But I would like to keep that to office hours. So yeah, because I think there's two people who are like either sick or had tech issues and weren't able to get in. Today I'm not going to run through solutions of the exam. Of course, the makeup tests will be different, but they're similar enough in structure that I don't want to give too much away because everybody else had to come in blind. But the exam, I will have the scores. So exam 1 will be graded no later than 1 week from Monday. So 1 week from the 22nd, i.e., what is that? It's the 29th, right? So I'll have your grades in by 6/29 at the latest. If I get them done sooner, I will put them in sooner. But grading things online like this is kind of a pain in the ass. Since I don't have a tablet, I can't annotate directly. I have to print your stuff, write comments on it, and then scan it back in, and all that takes time. But I promise I'll get those grades turned around. If there's anything you're curious about or any particular questions you want to ask, reach out to me and I'll be happy to talk with you about them. We can either do it through Canvas or in an office hour. I do have a normal office hour today from 1 to 2. The material that we're about to cover we're going to begin the discussion on convergence. And this is a big, big, big deal. So you may remember me saying at the start of the term that this course is basically split into 3 pieces. The first piece is how to integrate, the middle piece is convergence, and the last piece is applications. The middle piece, you see the big gesture here, is the heart of the class. Convergence, to put it simply, is possible outcomes of infinite processes. And you get a smell of this in Calc 1, right? In Calc 1, you play around with the notion of infinity every now and then. You talk about limits at infinity. You talk about limits having value infinity. You talk about getting as close as you want to something. All of those are sneaky ways of getting around this concept of infinity. In Calc 2, we're gonna grab it whole hog. A few names that you might want to Google, people you might want to research a little bit. First and most important in my mind, Georg Cantor. He wrote a book called Philosophy and Mathematics of the Infinite that was hugely influential. Unfortunately, and this was not that long ago, BT dubs, this is around the time of Niels Bohr, just before the Copenhagen Revolution in quantum physics, at a time when mathematics was thought to be very solid. But then we started asking some questions about infinite sets that led to the feeling that maybe it's not so solid. And so there was this crisis. And Georg Cantor was kind of the man who pulled out pulled the sheet out from underneath and showed that everything was really kind of standing on air, that there really wasn't much there. There's a great documentary about this guy and some of his contemporaries. I recommend the documentary Dangerous Knowledge. I think it's available on YouTube for free. Double check. Yeah, that's it. Check it out. It's really, really good. They interview Gregory Chaitin and a few other contemporary mathematicians who extended Cantor's work. Unfortunately, he ended up dying quite insane after working very, very hard on a particular problem having to do with infinite sets. Another big name here you may know is Augustus Cauchy. His Wikipedia page is definitely worth a read. And also Weierstrass. So these were the guys who around the turn of the 20th century started, in fairness, Cauchy came a long time before then, but these are the guys who in the late 1800s, for the most part, put mathematics on a relatively stable framework rather than just like guessing or this feels right. They started proving things having to do with infinite processes, which is a tricky, tricky business. So all of that is to say, some very brilliant people worked very, very hard for a very, very long time to discover what we're about to learn. So you should expect it to be fucking hard. And it is. It's very hard. But if you put the time in, and especially if you take the time to talk to people about it, this is the big thing, because there's so much vocabulary and it's so concept dense that just practicing calculations won't be enough. You're going to need to practice talking about these things too. The main objects we're going to study here are indefinite integrals, which is the section we're going to start on today, sequences, which is section 11.1, and series, which covers sections 11.2 through 11.10. Series are probably the scariest part of Calc 2 for most people, and we'll be able to relate them back to indefinite integrals in a way that I hope will help you feel a little bit comfy. So we'll begin with this idea of an integral, and then we'll extend to the other ideas. I think that's enough background. Question. What is the total area under y equals e to the negative x from x equals 0 all the way to x equals infinity? In other words, if I draw that graph of e to the x, or e to the negative x, sorry, we know what that looks like. It's like e to the x, but flipped around horizontally. Which means as we come out here towards plus infinity, it's settling down on the x-axis. So I want to find all of this area, if I can, right? That's the game. And this is, of course, infinite in length, right? This region has infinite length. And the question is, does that automatically mean it has infinite area? The answer is going to turn out to be no. The answer is going to turn out to be, it's possible to have something that's infinitely long, but with finite area. And you might ask, how the hell is that possible? Well, the answer is that the height has to get very, very, very small. So how do we do this? What is it that underpins this and allows it to go? It turns out that your regular integrals are going to work pretty well, but we're going to have to handle them a little bit carefully. So the answer here is going to be section 7.8, which is improper integrals. And the basic idea is that we take a limit of a regular integral. So let me redraw that picture a little bit bigger over here for you. I'm going to zoom in on the part that we care about. So I'll come up here and mark this as 1. That's my y-intercept. And we know that this graph just gets closer and closer and closer to the x-axis as we go out. Instead of trying to find all of the area right away in a single step, I'm going to pick my favorite real number, whatever, call it r. And I'm going to find the area from 0 to r. Once I have a nice formula for that, I can send r to infinity. So answer. First, find a formula for the area from x equals 0 to x equals r, then take the limit as r goes to infinity. That's the basic idea. So the area from 0 to r, which I'll call AR, that's the integral from x equals 0 to x equals r of e to the negative x dx. All right, we know that the area from a to b underneath the graph y equals f of x is just the integral from a to b of f of x. Therefore, the total area from x equals 0 all the way out to x equals infinity is a equals lim r to infinity a of r, which is the limit as r goes to infinity of the integral from 0 to r e to the negative x dx. We work this from the inside out. We work the integral, then take the limit. So the integration step here isn't hard. An antiderivative for e to the negative x is negative e to the negative x, and we're going to evaluate that from 0 to r, and then send r to infinity. So the limit is the last thing that we do. This is going to be negative e to the negative r minus negative e to the negative 0. That's 1 minus e to the negative r. And then, of course, as r goes to infinity, e to the negative r goes to 0. So this is 1 minus 0, which is 1. So you get the kind of astonishing fact that all the area underneath e to the x from 0 to infinity, that total area, even though it's infinite in length, is 1. Miraculous, right? Pretty astonishing stuff. It takes a while to wrap your head all the way around. We can also apply this to volumes. If I wanted to, I could rotate this region about the x-axis, and that would produce a horn-shaped object called Gabriel's horn. And we could try to find the volume of that infinitely long horn. Yeah, it's good stuff. So this really blew my mind the first time I saw it. And the first thing that we kind of have to wrap our heads around is this idea that there are objects of infinite length, but finite area. So something can stretch on and on forever if it's two-dimensional and have finite area. And the catch is going to be, it has to get really small as you go out this way, right? If there was some line that this always stayed above, then there would be some infinite rectangle in there. And that rectangle, whatever its height is, since it's infinite in length, it would have to have infinite area. So these functions, they have to decay to 0, but it turns out that that's not enough. They have to decay to 0 really fast. So that's the kind of high-level intuition. If your height shrinks fast enough, then your area might still be finite, even if your length isn't. There's two types of situations like this called improper integrals. They're called type 1 and type 2. Type 1 improper integrals are the one that we just looked at, where the length is infinite and the height is finite. Type 2 improper integrals are integrals where the height is infinite. And it's also possible to mix them. You could have something where the height and the length are infinite. And even there, it's still possible to converge. So this is the language that we're going to use. There was a question in chat, and it was asking, so if we sent R out larger and larger, if you tried to find this area by direct calculation, like if you had some area measuring tool and you wanted to do it by hand, yeah, the idea is as you let R be bigger and bigger and bigger and bigger, the total area enclosed here will get closer and closer and closer to 1. That's the idea. So we need some definitions and some notation. A type 1 improper integral is one where the length of the interval of integration is infinite. So for these, we have something like the integral from some number to infinity of f of x dx, or maybe something like from negative infinity to a of f of x dx. So either I'm asking for the area from some constant all the way out to infinity, or I'm asking for the area from negative infinity all the way up to some constant. And both of these are defined through limits. So this first guy is the limit as r goes to infinity, integral a to r of f of x dx. And this is an a down here. And this other guy I would define as the limit as r goes to negative infinity, integral r to a of f of x dx. I want to talk for just a minute about why we need these definitions, because it might not be entirely obvious at the outset, it just appears to look right. Imagine I tried to straight away build a Riemann sum for this thing. So remember all the shit that we did in chapter 7, really chapters 5, 6, and 7, it all depends on Riemann sums. Your integration by parts rule, your U substitution rule, your fundamental theorem of calculus, right? Which says that you can find an antiderivative and use that to get areas. All of that only works for continuous functions on closed bounded intervals, right? You need a continuous function on a compact set for that shit to work. You could never build a Riemann sum for something like this, because remember how your Riemann sums were defined. You started by partitioning your interval into a finite number of finite length pieces. You called those pieces delta x, and they were b minus a over n. If b is infinity, then b minus a is infinity, b minus a over n is infinity, so you cannot partition this interval into finitely many pieces of finite length. If you have finitely many pieces and they're each finite length, then you're not going to cover all of A infinity. So a note here, we can't build Riemann sums for integrals like these. Because delta x, which is b minus a over n, would be infinity minus a over n, would be infinity. So good luck. Right, we're screwed. There's no way to do those calculations and then come up with a formula for that sum and then take the limit as n goes to infinity. It just can't be done because you get stuck at the very first step. You get stuck at calculating delta x, which is why we have to define them through these limits. Fundamental theorem of calculus does not apply to this, but it does apply to this, because here I'm taking the limit later. This is a regular definite integral from a to r. R is just understood to be some constant. And then later I send r to infinity. This sneaks in after the fact. So this guy, I can apply my fundamental theorem of calculus to. I can do trig sub, U sub, IBP. I can use the FTC 1 and 2 as much as I want here, but I can't use them directly here. So this definition is a big deal. And the take home, to do an improper integral, you must first write it, whoop, not first, as a limit of a normal or proper, really the term is Riemann integral. So something happens as people start to get comfy with these problems. They start getting sloppy and stop writing these limits. Please don't do that. For this very important technical reason, I must dock points if you do that. Because if you try to apply your fundamental theorem of calculus directly to this object, you're breaking the rules, right? What you're doing is not mathematically sound, because FTC 1 and 2 do not apply to this integral, because this integral has no Riemann sum. The way we prove the fundamental theorem of calculus is through Riemann sums, or if you're in a slightly more advanced class, what we call Darboux sums. Or if you're in a slightly more advanced class, we call them Lebesgue integrals in measure theory. But all that shit requires this ability to partition. And we cannot partition an interval of infinite length. Okay. one more bit of notation, or I guess it's really vocabulary. This is why I'm saying it's so important that you talk about these things. If an improper integral has a finite fixed value, i.e., like the limit as r goes to infinity of the integral a to r f of x dx exists and is finite, then we say that the improper integral, the integral from a to infinity f of x dx, converges. Hamlet, be good. Sorry, my dog's looking a hot spot. Converges to that value, to the value of that limit. All right, so the vocabulary is very important here. We say the improper integral converges if this limit exists and is finite. Otherwise, we say the integral diverges. So just to play grammar Nazi for a minute, there's several different forms of this word, and they are different parts of speech. So I'm going to pretend like I'm your ENC 1101 teacher for a second. Converge is a verb. It's something we do. The integral converges. The integral converged. The integral is converging, right? Converge is a verb. Diverge is also a verb. It's something that the integral can do. There are nouns and adjectives associated with these also. So I can refer to an integral that converges as being a convergent integral. So while we're here, in this little vocab aside, converge, the word converge is a verb. So is diverge. The adjective form of converge is convergent. So is divergent. So I will refer to an integral that converges as convergent. It is a convergent integral if that integral converges. If that integral does the thing, which is to converge. Same for diverge and divergent. The way we use these is we say the convergent integral 0 to infinity e to the negative x dx, the one we did at the start, converges to the value 1. So that's the language and that's how we use it, right? Converge is a verb, convergent is the adjective, and when you want to refer to the value of a convergent integral, we use the word to. So I hear people say converges at or converges with, and it makes me cringe just a little bit. In the same way that, you know, we cringe when we hear little kids misuse words a little bit like that. I'm not going to beat you up for it, but just so you know, right? This is the language of the objects. And we're going to be using these words converge and diverge, not just for integrals, but also for sequences and for series and for power series. So it's important that you get comfy with using them. In other words, please talk with each other about this shit. I know it's hard to do that in the online setting. I do have the discussion boards open on Canvas. You can talk with each other there. I'm sure that you guys also have a GroupMe or a Discord or something going. If you don't, make one and talk to each other about these things, practice the vocabulary. You can of course practice it with me, but there's no replacement for just spending time talking about this shit. So the more you do that, the more comfortable you'll get with it. Any questions about the definitions or the kind of language here or any of that stuff? This is section 7.8. Yeah, no problem. Okay, so I want to get a little bit more practice with type 1 integrals, and then I will show you type 2 integrals. So I want to find all the area underneath f of x equals 3 over x squared to the right of x equals 1. Yeah, Nicholas, what you said is exactly correct. So it's a new bit of language to describe some very specific limits. And instead of talking about a function approaching a particular value, we're talking about an integral approaching a particular value. Yep. Yeah, in fact, you could define a new function in terms of the integral. I could call capital F of r the integral from a to r of little f of x. And then what we're really doing is taking the limit as capital R goes to infinity of f of r. It's kind of like the way you learned FTC2 back in Calc 1. Okay, so 3 over x squared, I know what he looks like. 1 over x squared looks like this, so 3 over x squared looks like this too. It's just scaled up. Here's this point, 1 comma 3. And I want to find all the area to the right. And it goes on and on and on forever. That area is equal to the integral from 1 to infinity of 3 over x squared dx. But before I can do anything with this, before I can pop out the 3, before I can do anything at all, I have to write it as a limit of a Riemann integral. That is an integral for which we can build a Riemann sum. And that's why I use the letter R in honor of the man. So that's always our first step. Rewrite as a limit of a proper integral, a proper definite integral. And then from there, we can start doing stuff. I can pop the 3 out. I could actually pop it all the way out past the limit if I wanted to. And then the 1 over x squared I write as x to the negative 2. And now since this is just a normal Riemann integral, I can apply my power rule. I'll add 1 to the power, divide by the new power. Don't forget to write your limits though. So when I add 1 to this power, it becomes x to the negative 1. So this is negative 1 over x that I'm evaluating between 1 and r. And you can check, negative 1 over x differentiates to 1 over x squared. I am going to go ahead and pop the 3 out. And I get 3 lim r to infinity. And now I evaluate this piece. I'll have negative 1 over r minus negative 1 over 1. I'll write it out. Why not? Negative 1 over r minus negative 1 over 1. Which is the same as 3 times the limit as r goes to infinity of 1 minus 1 over r. And of course, 1 over r goes to 0 as r goes to infinity. So we just get 3 times 1, which is 3. Therefore, I would say the improper integral integral 1 to infinity 3 over x squared dx converges to, so it's the verb converges because it's what the integral is doing, and it's converging to something. The thing it's converging to is 3. In other words, the total area there is 3. Yeah, so in other words, the total area under f of x equals 3 over x squared to the right of x equals 1 is 3. But it's the language of converge and diverge that we want to start getting comfy with. So improper integrals are the first object we're going to meet for which convergence is a relevant question. But these are not the only kind of improper integrals. There are also type 2 integrals, where the height is infinite. You can imagine here, if I wanted to integrate from 0 to 1, then the height would be infinite, and I have another problem to deal with. And we'll talk about how to deal with that. And then we'll see also how you can mix these things together. Questions on this example? Okay. Oh, yeah, I see something in chat there. No, that's just a scratch. Sorry, I started to write the wrong thing. Yeah, so Ryan asked, is that a 0? No, I just started writing the wrong word. So I want to play a similar game here. Only this time I'm not going to parse it in terms of areas. I'm just going to ask us to evaluate an integral. So I'm going to reuse this page. If you're writing in your notes, just start down here. Let's evaluate integral from 1 to infinity 1 over x dx. So I would start by writing that as the limit as r goes to infinity, integral 1 to r, 1 over x dx. And you know, the picture here is more or less the same as the last one. It's the same sort of shape. It's this like hyperbolic looking thing that settles down on the x-axis, so that here my height is going to 0 as I go out to the right. Over here we have this piece, but really we're looking for like all this area. So it looks a lot like the last one, but we're actually going to get something different here because the antiderivative is different here. Antiderivative for 1 over x is the natural log of x. So this will be lim r to infinity natural log of r minus the natural log of 1. ln of 1, of course, is 0. So what happens to the natural log of r as r goes off to infinity? Does anybody remember that? A few ways to think about it. Let's look at the graph. All right. So here, if you zoom out, it looks like it might have a horizontal asymptote. But if you keep zooming out, you keep going over, he actually keeps going up. He goes up very slowly, but he never stops going up, and he never gets bounded above. So as r goes to infinity, the natural log of r also goes to infinity. And this is one of those limits. If you forget it from the limit at infinity section in your Calc 1 class, that's forgivable. This is infinity. So what I would conclude, I would say, therefore, the integral integral 1 to infinity 1 over x dx diverges. Or you could say is a divergent integral. Right, that's the verbiage. So there's something that we're starting to see. Oops, sorry. The chat window go, god damn it. There it is. Thomas asked a good question. Would we say diverges to infinity? You could say that if you wanted. I wouldn't be against that. But really, if an integral diverges, I'm kind of no longer interested in it, at least for our class. Now, there's this great book called Divergent Series that was put together by Srinivasa Ramanujan and then edited later, which is wonderful. There's all sorts of cool shit you can do with divergent objects. But in this class, for us at the Calc 2 level, if it diverges, we're done. I don't particularly care anything beyond the conclusion of divergence. But if you want to specify diverges to infinity, diverges to negative infinity, diverges by oscillation, that's okay too. Yeah, I wouldn't be upset or say that that is incorrect language at all. So let me do one more little calculation here. And then we're going to look at some graphs, and we're going to make a neat observation. Actually, let's do two more. Value 8, integral 1 to infinity, 1 over x to the 0.9, and integral 1 to infinity 1 over x to the 1.1. Yes, so Ryan asked that previous integral, would I say that that integral is divergent? Yeah, that's exactly what I would say. I would say that is a divergent integral. So here, this guy I'll write as the lim as r goes to infinity, integral 1 to r, x to the negative 0.9 dx, which is lim r to infinity, x to the negative 0.9, that's a power rule integral. I'm going to add 1 to that power and then divide by that new power. If I add 1 to negative 0.9, then I'm going to get positive 0.1. So this is x to the 0.1 divided by 0.1. evaluated between 1 and r. I can pop the 1 over 0.1 out, and I get lim r to infinity, r to the 0.1 minus 1. Now, r to the 0.1, 0.1 here is a positive power. So as I take bigger and bigger numbers and I raise them to the positive power 0.1, those get bigger and bigger and bigger. So this is 1 over 0.1 times plus infinity minus 1. Infinity minus 1 is still infinity. Infinity divided by 0.1 still infinity. So this is infinity. Therefore, or hence, the integral 1 to infinity 1 over x to the 0.9 dx diverges. And now on the other hand, this guy is the limit as r goes to infinity, integral 1 to r, x to the negative 1.1 dx, which is again a power rule thing. If I add 1 to the negative 1.1 power, my antiderivative is shown to be x to the negative 0.1 divided by negative 0.1. I can pop that negative 0.1 over here out, and I'll have negative 1 over 0.1 times the limit as r goes to infinity of r to the negative 0.1 minus 1 to the negative 0.1 is still 1. Here's the interesting thing, this power is negative. So this is negative 1 over 0.1 lim r to infinity 1 over r to the positive 0.1 minus 1. And now as r goes to infinity, this power of r will go to infinity. So I get 1 over infinity minus 1 there. So this is negative 1 over 0.1 times 1 over infinity minus 1. And again, I'll remind you, 1 over infinity, your calc 1, that's 0. So this is negative 1 over 0.1 times 0 minus 1, which is just positive 1 over 0.1. So this integral converges. It converges to 1 over 0.1, but mostly I'm interested in the fact that this guy converges and the other guy diverges. And the question is, what gives? So we've seen that the integral of 1 over x from 1 to infinity on his own diverges. If you take 1 over x to a power slightly smaller than 1, that's also divergent. If you take 1 over x to a power slightly larger than 1, that's convergent. We've also seen that the 1 over x squared integral converges. So you get the feeling that something special is happening with 1 over x. There's some sort of tipping point there. And I want to show you in Desmos what I'm talking about. All right, so I'm going to put this guy in black. And I'm going to zoom in on the good stuff here. The good stuff for us is this stuff. Notice that from 1 to infinity, the blue here is smaller than the black. That's 1 over x to the 1.1. That's the guy who we just found converges. We've also looked at 1 over x squared. I'll put him in that same sort of purple. So you can see that the guys here who we saw their integrals converge, they all live below the black, at least from 1 to infinity. What about the guys we saw who diverged? Well, that was besides 1 over x, that was 1 over x raised to the 0.9. So if you're above the black, you enclose more area than the black curve, which means you diverge. And if you're below the black, that doesn't guarantee that you converge, but definitely if you're below this guy, you converge, because we know this guy converges. And we're thinking about how much area there is here. So the black curve, 1 over x, is a special tipping point. This leads us to a theorem, and it's our first important theorem on convergence tests, called our theorem on p integrals. So we have this theorem. First, integrals of the form integral a to infinity 1 over x to the p dx, where a is positive and p is any constant. They converge if p is strictly greater than 1, and they diverge if p is less than or equal to 1. So the bigger the power p here, the faster the denominator grows, which means that this whole function will shrink to 0 faster. So the larger the value of p in this integral, the easier it is for this area to be finite. These are called p integrals. So another way to say this is p integrals converge if p is strictly bigger than 1, and p integrals diverge if p is less than or equal to 1. Hey, Bobo. It's okay. You're a good boy. All right, my dog's looking at me all scared. So this is our first big theorem. It's a good theorem. It's awesome. P integrals are integrals of the form 1 over x to the p, and they're type 1 integrals. So they have to be going from some positive number to infinity. Those integrals will converge if p is bigger than 1, diverge if p is less than or equal to 1. And it's worth remembering that. In fact, it's crucial that you remember this. We're going to use it a lot. The proof is not a lot of fun. It's just the same calculation that we did in those last 3 integrals, only I split it up into cases based on p. If you want to go through the proof carefully, your book does prove it. It's example 4 on page 530. I can walk you through it quickly here. Actually, let's do it like this. Where is it? Here we go. Oh, no. Not that. Yeah, kind of that. Okay. So here's the proof. They ask, for what values of p does the integral converge? Or for what values of p is the integral convergent? We know that if p equals 1, the integral is divergent. So because we've already done that, the integral 1 over x. And then they say, assume p is not equal to 1. So you can use your power rule. Here's the calculation, right? It's a straightforward power rule calculation. You add 1 to the power, divide by the new power. They're using the symbol here, t instead of r. That's okay. Negative p plus 1, that's the same as 1 minus p. And so you get this. Now we need to send t to infinity here. If I want to send t to infinity, I need to know whether p minus 1 is positive or negative. If p is bigger than 1, then p minus 1 is bigger than 0. So this piece, the 1 over t to the p minus 1 piece, would go to 0, and you get this finite value out. But if p is less than 1, then 1 over t to the p minus 1, that power is really negative, so that thing really belongs upstairs. And so this piece would go to infinity as t goes to infinity. So that's it. You might want to go through this slowly and carefully by yourself, especially these last bits. But it's not terribly hard to see, especially when you think of the graphs, right? We know 1 over x here, the area underneath the black curve is infinite. We know that the area underneath both of the purple curves is finite. And we know that if you use a larger or larger power, then that curve will sit down even harder on the x-axis. For example, if I look at 1 over x cubed, he lives underneath both of the purple curves. So if the area underneath the purple curves is finite, then the area underneath the blue curve has to also be finite. That's the nice way to think about it. Questions on this theorem or the concepts that kind of underlie it? Okay. So I think you have a reasonable feel for these things. If you want to do a type 1 integral, you write it as a limit of regular, finite, nice, normal, no problem integrals. Calculate your antiderivative, and then take the limit after evaluating. But things are not always so nice. Sometimes your integral has other problems, like Ryan, I would caution you on the language there. If any function converges, then it is finite. So it's not the function converging that we're talking about. It's the integral converging. If a function gets small sufficiently fast, then a type 1 integral of that function will converge. And it's going to be hard to be very precise about that beyond what we have here without a few more theorems. So I'll ask you to hang in with me as we go a little bit further. But here is a useful theorem. We'll just call it the comparison theorem for improper integrals. And I'm going to walk you through it for type 1 integrals, but you can also use it for type 2 integrals. We just haven't talked about them yet, but I think now is the right time to talk about it. Suppose f and g are continuous and 0 is less than or equal to f of x is less than or equal to g of x. Right, so the graph of f is everywhere underneath the graph of g. Then if the area under g is finite, the area under f also has to be finite. In other words, if the integral from a to infinity of g of x converges, no. You guys are so not. Here. Go. If this integral is finite, i.e. converges, then so does the integral of f. Because f is smaller than g, the area under f is completely enclosed by the area under G. So if you fit inside a finite box, you must be finite. Here, if F is smaller than G, says the area under F fits inside the area under G. So if the area under G is finite, i.e. that integral converges, then the area under F is finite, i.e. that integral converges. Also, if the smaller integral diverges, then so does the larger integral. So if you fit in a finite box, you are finite. And if an infinite box fits inside you, then you are infinite. Make sense? Okay, so I want to give you an example here where we can deduce the convergence from our theorem and then also calculate the integral. So we could say determine whether integral 0 to infinity 1 over 1 plus x squared. Actually, let me do this from 1 to infinity, sorry. Integral 1 to infinity 1 over 1 plus x squared dx is convergent or divergent. It's very familiar with the squeeze theorem, yes. In fact, what you're doing here is you are squeezing the integral of f between 0 and the integral of g. The way you prove that comparison theorem is using the squeeze theorem. That's a good observation. One way we could attack this problem is by computing the integral. It's not a hard integral. It's an arctan thing. But that's not the only way to attack it. We could also use the comparison theorem. We could say, observe that 1 over 1 plus x squared is smaller than 1 over x squared. Why? Because its denominator is bigger. Bigger denominator, smaller overall. And also, 1 over 1 plus x squared is bigger than 0. Why? Because x squared is always positive. 1 plus something positive is positive. So we have this inequality. And integral 1 to infinity 1 over x squared dx is a convergent p integral. Because here p is equal to 2, which is definitely bigger than 1. Therefore, integral 1 to infinity 1 over 1 plus x squared dx must converge by the comparison theorem. Job done. So without any computation, I know that this integral converges. A word of advice. You're going to want a few pages in your notes dedicated to convergence tests. These are the only two convergence tests we're going to have for improper integrals. We've got our P integral theorem and our comparison theorem. You're also going to have a bunch of convergence tests for sequences and a bunch of convergence tests for series. And you're going to want one place in your notes where you can organize all this shit. And you do not want to confuse the tests for sequences with the tests for series with the tests for integrals. So I would have maybe even outside your notes in a special little notebook or something, a place where you just talk about convergence tests and where you get all this shit organized. For section 7.8, you want your comparison test and your p-integral test. Those are your two big friends. Yeah, so what Nick asked in chat there is if we can relate the function that we're trying to figure out, his integral converges, like here, the 1 over 1 plus x squared function, to another function whose convergence or divergence when integrated over that same range is known, then you can make a conclusion about yours. So here I say, oh, well, my function is smaller than 1 over x squared, and the integral over that same place from 1 to infinity of 1 over x squared is known to be convergent because it's a p-integral. I can conclude that my integral must also converge. Yeah, that's exactly the idea. Another valid approach here, just compute the damn thing. Integral 1 to infinity 1 over 1 plus x squared dx is the limit as r goes to infinity, integral 1 to r, 1 over 1 plus x squared dx. Now that's not a power rule thing anymore. I'm going to grab some water real quick. It's not a power rule thing anymore, and it's not a p-integral. It's not a straightforward power of x. But what we can do, this is arctan, remember. You could do the trig sub here if you forgot. But remember that 1 over 1 plus x squared, that's the derivative of the inverse tangent function. So the integral of 1 over 1 plus x squared is the inverse tangent of x evaluated between those bounds, 1 and r. So that's equal to the limit as r goes to infinity of the inverse tangent of r minus the inverse tangent of 1. Who remembers arctan of 1? Anybody? Yeah, okay. I see it in chat here. Let's see. We got, damn, this thing keeps doing that. Yeah, pi over 4. Very good. And what about the limit as r goes to infinity of the inverse tangent of r? Good, yeah, pi over 2, right? The horizontal asymptote as you run off to the right on the graph of arctan is pi over 2. So this is pi over 2 minus pi over 4, which is pi over 4. Since this is finite, we can conclude converges, and it converges to pi over 4. So the advantage of the bottom method is that it tells you the value of the integral. The top method just tells you that the integral converges. Remember the limit as x goes to infinity of inverse tangent x is pi over 2. So this is coming from the horizontal asymptote of arctan. Here's arctan. Here's the line y equals pi over 2. And you see that he sneaks up on him. So this is one of those limits that ideally we should remember from Calc 1. On the other side, he approaches negative pi over 2. Damn it, come on. Yeah. So these are things that you want to remember about the inverse tangent function for sure. Cool. Okay, so the advantage to this is that it tells me the value of the integral, which is more information than I get here. This just tells me that the integral converges or has a finite value, but it doesn't tell me what that finite value is. So when possible, you want to do this. When possible, you want to calculate the integral. Sometimes this is easier. Sometimes this is easier. Usually this is easier, but it depends on how easily you can come up with a nice inequality. You may have noticed when I first started to write this problem down, I wrote it with a 0 as the lower limit. And the reason I changed that is because this first approach would be problematic because the integral from 0 to infinity of 1 over x squared is not a p integral, because it's not a type 1 integral, because 1 over x squared has a problem at 0. So that's the next thing I want to talk with you guys about, is how to handle type 2 integrals. Oops, I looked and didn't look. 1244, okay. So I'm going to introduce the concept of a type 2 integral now. If f of x has an infinite discontinuity at x equals a, then the integral a to b f of x dx, or integral c to a f of x dx would be called, or are called, type 2 improper integrals. So we want to see what we can do about integrating through a vertical asymptote. That's the idea. And the problem that you run into is very similar to the problem we just dealt with, in the sense that this area could be infinite, because the region whose area you're measuring is infinite in at least one of its dimensions, here infinite in height. So a nice example, let's look at the integral from 0 to 2 of 1 over x minus 2. We know what the graph of 1 over x minus 2 looks like. It's the same as the graph of 1 over x, just shifted to the right 2 units. So we have a vertical asymptote here. And then aside from that, we look like 1 over x. So it's like this. And I want to integrate from 0 to 2, which means I've got problems here. So if I want to do that integral, I need to do something special, because just like I can't build a Riemann sum for the other guy because delta x is always infinite, I can't build a Riemann sum for this guy because f of 2 is infinite. The way we define these, so I'm going to come back to this example, the way we define these is by taking limits. So if f of x has a infinite discontinuity at a, then we write limit as r goes to a, integral r to b f of x dx. That's for this first guy, or integral limit r to a, integral c to r f of x dx. So in other words, you sneak up on the discontinuity. So this guy I would write as limit r approaches 2 integral 0 to r 1 over x minus 2 dx. Now there's a little micro u sub in here that I'm going to do quickly. The antiderivative we get out, oh, limit r to 2, sorry. Screw this here. Let me take this whole example to the next page. So if f of x has infinite discontinuity at x equals a, then we write the integral from a to b of f of x dx as the limit r goes to a, integral r to b f of x dx, and that's the definition. Now we'd write the integral with the problem on the upper bound, integral c to a f of x dx as limit r to a integral c to r f of x dx. So that's our definition, and these are called type 2 integrals. So for example, if I wanted to integrate from 0 to 2, 1 over x minus 2 dx, I would write that as the limit as r goes to 2, integral 0 to r 1 over x minus 2 dx. And then I take my antiderivative. This is going to be limit r goes to 2, natural log absolute value x minus 2 evaluated from 0 to r. So it's the same as the limit as r goes to 2 of ln absolute value r minus 2 minus ln absolute value of negative 2, which is lim r to infinity ln absolute r minus 2 minus ln, the absolute value of negative 2 is just 2. But the tricky bit is this limit. Oh, sorry, and I wrote that infinity again. It's a habit. I'm sorry. R is going to 2 there. As r goes to 2, r minus 2 goes to 0. And as its inside goes to 0, the natural log goes to negative infinity. So we get negative infinity minus ln 2, which is still negative infinity. So this integral, this type 2 integral, diverges. Sorry about that, got a little bit cluttered. I forgot to write down your limit definitions before I started the example. I was just so excited. So if your function has an infinite discontinuity and you're trying to integrate over some region that contains that infinite discontinuity, then you need to sneak up on that infinite discontinuity using a limit. Yeah, so we were here. So if you have an infinite discontinuity at x equals a, and you're trying to evaluate an integral either from a to somewhere else, or from somewhere else to A, then those are called type 2 integrals. This first guy we would treat as the limit as r goes to A, integral r to B. And the second guy we would treat as limit r to A, integral c to r. So things got a little bit messy here. That's why there's nothing over here that isn't on the other page. So if it's okay, I would actually prefer, this is what we should have in our notes. And these are called type 2 integrals. Type 2 improper integrals. You'll notice that both of these integrals have the problem spot at an endpoint. And so did our example. The problem spot here was 2, and it was at an endpoint. So the kind of natural questions to ask from here is, how do we handle a problem spot showing up in the middle of our interval? And what happens if I mix type 1 and type 2 stuff? So I'd like to look at another example now, and I think you'll find this useful. What if I want to evaluate the integral from -1 to 1 of, let's see, what could we do here? I'd like to do 1 over root x, but I can't. We could do 1 over the cube root of x, maybe? Yeah, let's try that. So if we want to have the previous example still visible, yeah, I can do that here. Let's see, how's that? We'll just wait a minute here. I'll just leave this up. You guys can finish writing. I don't want to rush you. So this last example, integral 0 to 2, 1 over x minus 2. First, we write it as a limit. Our problem spot was the 2. So I take the limit as r approaches 2, and then I do the integral 0 to r. 1 over x minus 2 has as its antiderivative natural log absolute value x minus 2. And then I evaluate that between bounds. When I plug in r, I get ln r minus 2. When I plug in 0, I get ln absolute value of -2. Here, the ln r minus 2 doesn't change. The absolute value of -2 is 2, so that's all I did there. And then as r approaches 2, the ln of r minus 2 is approaching the ln of 0. The ln of 0 is -infinity. So this is -infinity minus the ln of 2. Because as his inside goes to 0, natural log goes to -infinity. Picture that graph of ln x. -infinity minus ln2 is still definitely -infinity. So I would say this type 2 integral is divergent or diverges. I'll give just a second or two more. I apologize. I got a little bit disorganized there. We all good? All right. So let's look at the integral from -1 to 1 of 1 over the cube root of x squared. Let's do that. Oh, actually, sorry. We'll just do the cube root of x. What the fuck? Yeah, we'll do it like that. hard to come up with good and exciting examples here that aren't overwhelming. This will be a worthwhile thing. So here the problem spot, f of x equals 1 over the cube root of x. This has a problem, an infinite discontinuity, at x equals 0. And 0 is between -1 and 1. So the problem spot here isn't at one of the endpoints, but it is in the interval I'm dealing with. The way you handle this is by splitting up the integral. So we do the integral from -1 to 0 and the integral from 0 to 1 separately. We compute each of those using their own limits, and then we add them up. I know this has an infinite discontinuity at x equals 0 because the denominator is 0 when x is 0. Yeah, the cube root of 0 is 0. So 1 over 0, that's like infinity. If you like, you could look at the graph. But we should know the graphs of these power functions pretty well. So 1 over x to the 1/3. I'm going to give something away here, but you see it, right? This thing blows up to infinity at x equals 0. So the way we're going to do this is by splitting the integral, -1 to 1, 1 over cube root x, as integral -1 to 0, 1 over cube root x, plus integral 0 to 1, 1 over cube root x. And now each of these looks like our normal type 2 improper integrals, where I've got a problem at the end point. Something you do need to remember is that they each get their own limit with their own variable. So this first one I'll call the limit as r goes to 0 from the left, because I'm trying to sneak up on the infinite discontinuity from the left. Because here it's -1 to r, 1 over the cube root of x dx. So I'll draw a schematic here in just a second. This guy, I want to sneak up on this, sneak up on this problem point. And since I'm looking on the interval 0 to 1, I need to sneak up on it from the right. So I'll say here, s is going to 0 from the right. Integral s to 1, 1 over the cube root of x dx. So if we come back and look at these Desmos graphs, the first integral is trying to deal with this piece. And the idea is I want to sneak up on the discontinuity here at 0, where I'm diving off to -infinity. And in order to do that, I'm just looking from -1 to 0. That means I'm sneaking up from the right. And that's that one-sided limit there. Sneaking up on 0, from the left. That's that one-sided limit there. So I'm coming towards this discontinuity from the left. So in this first integral, I use a limit as r goes to 0 from the left. In the other integral, the integral from 0 to 1, I'm sneaking up on that discontinuity from the right. So for this integral, I'll use the limit as s goes to 0 from the right. Hence the one-sided limit thing. Now each of the integrals is fairly easy, or each of the antiderivatives is fairly easy. This is x to the -1/3. So if you add 1 to -1/3, that's -1/3 plus 3/3 is 2/3. So this is 3x to the 2/3 over 2, evaluated from -1 to r. And this guy will be the same antiderivative, just with his own limit. Limit s goes to 0 plus 3x to the 2/3 over 2, evaluated from s to 1. This is lim r to 0 minus. I can keep the 3/2 out if I wanted to. Maybe I'll write that like this so I don't have to fuck with it here. And then inside here we'll have r to the 2/3 minus -1 to the 2/3. That's that first guy. And the other guy, lim s to 0 plus, I'll do the same thing, pop out the 3/2, and then we'll have 1 to the 2/3 minus s to the 2/3, like this. Now, as r goes to 0 from the left, what does r to the 2/3 do? What is 0 to the 2/3 power? Oh, well, that power is positive. So this isn't a problem. 0 to the 2/3 is 0. So this becomes 3/2 times 0 minus -1 to the 2/3. Anybody got a feel for that guy? What's the cube root of -1 all squared? The cube root of -1 is -1. -1 squared is +1. So that first piece looks like this. Yeah, good. And then the second piece, again, as s goes to 0, this time from the right, s to the 2/3, 2/3 still a positive power, 0 to the 2/3 is 0. So this is going to be 3/2 times 1 to the 2/3 is 1 minus 0. And something interesting happens here. First, the integral converges because both of these are finite. This is finite. This is finite. So the integral -1 to 0, f of x dx converges. And this tells me that the integral 0 to 1, f of x dx converges. What's more, this is 3/2 times -1, that's -3/2, plus 3/2 times +1, that's +3/2. This whole thing equals 0. So since each piece converges, the whole integral converges. Moreover, the value of the whole integral, -1 to 1, 1 over the cube root of x dx, is 0. And there's a few little things I'd like to talk about here. First, any questions on the computation themselves? So we'll talk about the bounds. At the end here, I wrote, since each piece converges, meaning each of these two integrals here converge, the whole integral converges. And that's something I want to talk about in a second. There are some rules that can save you some time. And then below that I wrote, moreover, the value of the whole integral, integral -1 to 1 over the cube root of x dx. Sorry, I don't know why, for some reason the resolution on this computer is not as nice when I plug this camera up to it. Moreover, the value of the integral from -1 to 1 over cube root x dx is 0. Remember what we were trying to do. Our goal here was to evaluate that integral from -1 to 1 over the cube root of x. So we split it as the integral -1 to 0 plus the integral 0 to 1 because we had an infinite discontinuity at 0. So that's where our bounds come from, -1, 0, and 0, 1. And then each one of them we write as their own limit. Since the problem point here is the upper limit, this guy is written limit from the left. So I'm sneaking up on this 0 within the interval -1 to 0. And this guy I write as limit s goes to 0 plus, in other words, from the right. Because again, I want to sneak up on this problem point, staying within the interval 0 to 1. And then from there, we just took antiderivatives and evaluated the limits by plugging in, and then added up the two little integrals to get the whole integral. So a few little comments. So when we write improper integrals of type 2, where the problem is at one of the endpoints, we use one-sided limits. If f of x has infinite discontinuity at x equals a, then I would say the integral from a to b of f of x, really we should be using a one-sided limit here. It's the limit as r goes to a from the left, from the right here, because it's the bottom limit, integral r to b of f of x. Because the idea is I'm integrating from a to b, and I have this vertical asymptote here at a. Maybe b is out here somewhere, I don't know. I want to sneak up on that vertical asymptote by chopping here at r, and then letting r drift over like this from the right towards that VA. If the function has an infinite discontinuity at x equals b, then the integral a to b I would write as the limit as r approaches b from the left, integral a to r, f of x dx. Because here my problem point is on the right-hand side, maybe something like this. Maybe a is over here. So I want to sneak up on him from the right, from the left. That's the idea. So here I let r drift towards b from the left because I'm not interested in what's going on over here. And here I let r drift towards a from the right because I'm not interested in what's going on over here. So really when we write these, we want to be using these one-sided limits. And then if your problem is in the middle between a and b, you have to split the integral into two integrals and handle each problem point like this. And that's what we did in that previous example. Make sense? Yeah, yeah, it's a little bit weird. It takes a little bit of getting used to. How are we doing on time? 1:13. Oh, we're way over. All right. So I'm going to go ahead and stop the lecture here for today. I will get working on grading your tests. I'll have the grades in no later than a week from last Monday, so the 29th. I know that at least one person still needs to take a makeup test, so I've not gone over the questions here, but I'll do something like posting a key as soon as I can. And if you have any questions, you want to chat with me, just come on over to the office hour. All right, I'm going to go ahead and stop here. If I don't see you guys in the office hour, I hope you have a lovely rest of your day.